A confirmation regarding the audio, please, guys. If you're able to hear me out perfectly well, kindly confirm the same. Thank you. We shall be starting in a couple of minutes. So, hello, good evening to all of you, and welcome to Baiju's Exam Prep. Welcome to the second session of Geography, where we shall be picking up the threads that we left around in the first session, and then we shall be carrying on. So, basically, what is it that we had studied in the first session? So in the first class, we took a look at few of the very basics, right? So in the basics, we started taking a look at, for example, how is it that the universe came into existence? We took a look at the entire aspect of the Big Bang theory. That what do we mean by the Big Bang theory? And why is it referred to as the Big Bang? And how Big Bang theory basically holds the theory about or the description about the genesis and the formation of our entire universe. Now, that is something we had looked at. Then we took a look at Earth as a planet. Now, Earth is a planet present in the solar system, and it is the third most distant planet, or rather, the third most nearest planet from the Sun. And hereby, Earth is always tilted on its axis when it carries out its rotation. The tilt is at an angle of around 23.5 degrees from vertical, around 66.5 degrees from horizontal. That is the tilt of the planet that you come across. Now, here, when we have taken a look at the planet, we also know that because of the tilt, different parts of the planet, they experience varying length of daytime and varying length of nighttime. Because not only is the planet rotating around its axis, but the planet is also moving around the sun in a kind of a revolutionary axis. It revolves around the sun, and it revolves around the sun in an orbit which is elliptical. It is not circular, it is elliptical. That means it is slightly elongated. Now, the positioning of the planet in various parts of the orbit, that ensures a position whereby in certain cases you experience that the northern hemisphere appears to be tilted towards the sun. Now, when the northern hemisphere appears to be tilted towards the sun, that means it is summer in the northern hemisphere. And during those times, the daytime will be longer, the night time will be shorter. Now, when the northern hemisphere appears to be tilted towards the sun, the southern hemisphere, that gives an appearance as if it is tilted away from the sun. And being away from the sun means that lesser amount of heat, and hence you have shorter days, longer nights, and hence a winter season. So that is how we experience different seasonalities, different and varying length of daytime and nighttime, all of that based upon and dependent upon the position of the planet around the orbit of the sun. Now, it also happens that because the orbit is elliptical, that in one position on that orbit, the Earth and the sun's distance, that is minimum. And again, there is a position on the orbit where the distance between the sun and the earth becomes maximum. Because had it been a circular orbit, at all different positions, the distance between the earth and the sun would have been the same. But it is not a circular orbit, it is an elliptical orbit. Being an elliptical orbit means in certain location, earth is closest to the sun. And that position when the planet is closest to the sun, that is what we refer to as perihelion. You also have a position on the orbit where the Earth is farthest away from the Sun, and that position is what we refer to as aphelion. Similarly, as the moon keeps on moving around the Earth, in one position, moon is also farthest away from the Earth. That is what we refer to as apogee. And also, there is a position where the moon is closest from the Earth, and that is what we refer to as perigee. After that, we had started taking a look at the imaginary lines which have been drawn or which are drawn generally across the planet. Now, in the case of the imaginary lines, we have both horizontal as well as vertical lines. Now, the lines or the parallels which are drawn in a kind of a left to right or right to left format across the entirety of the circumference of the planet, those are referred to as latitudes. The largest latitude is the equator, and it is referred to as the 0 degree latitude. Then, as you move to the northern hemisphere, equator in itself divides the planet into two halves, that is the northern hemisphere and the southern hemisphere. As you move into the northern hemisphere, thereby the latitudinal angles they change depending upon the angle that the latitudes make with the equator. So that is how the latitudes keep on changing. And latitudes always they have served the purpose of ensuring a healthier navigation or smoothing the navigation process even during the ancient times. That is why latitudes have always been in use. Then we also studied about longitudes. Longitudes are basically circles drawn around the planet where the circle does pass through both the north and the south pole. So, like this, you have circles covering the entirety of the planet. Now, when you consider a circle, it will pass through both the north and the south pole. But that circle will have two parts, north to south on each side, isn't it? So those halves of longitudes, they are referred to as meridian. And that meridian is used as a reference point to take a look at timekeeping exercise as well. Whether you are able to understand that, for example, if it is 5 p.m. in India, what would be the time in Britain, and so on. So longitudes, they also serve that purpose. The meridian passes through which passes through Greenwich Royal Observatory near Greenwich. That meridian has been chosen as the reference point or the reference meridian, and it is referred to as the 0 degree longitude or the prime meridian. So obviously, the one which is going to be exactly to the opposite of that, that will be referred to as the 180-degree meridian, which is opposite to the 0 degree meridian. That is referred to as 180-degree meridian, which is also referred to as anti-meridian. And each of these meridians, they represent a time change. They represent a change in time in the case of referencing of time, which helps you understand the relative timing which is present or which is observed across the entirety of the planet. Okay. Now, then we come to the portion of international dateline, and thereafter we shall be moving on into the portion of the formation of planet Earth. So before that, when we talk about international dateline, what do we mean by international dateline? Now, this international dateline, basically, the name in itself tells you. Let's suppose I don't know anything about what do we mean by international dateline. So the name in itself tells me something to do with date, right? Date is what? For example, today is 9th March, yesterday was 8th March, like that date aspect. So basically, the international dateline, that is a particular line which delineates the occurrence of one day and then the occurrence of another day. So that is something which is delineated by the international dateline. So here, it is an imaginary line on Earth's surface defining the boundary between one day and the next. Now, if you can observe this image here, observe that this is the prime meridian, 0 degree longitude, or what is also referred to as the prime meridian. Now, in this case, if you will observe that here you have certain markings which are given, +1, plus 2, plus 3, plus 4, plus 5. What are these? These represent the timing. We do know that when we talk about the planet is the one which rotates from west to east. So that means if this is the sun, planet will be rotating from west to east. So the eastern portion will always experience the sunrise first. That is why you would have heard about the thing that sun rises in the east, sets in the west. So the eastern portion will always experience sunrise at an initial point in the initial stage. So that is why you will see that Japan is referred to as the land of the rising sun. Now, all of these meridians which are there, they represent different time zones, right? They end up representing different time zones. Now, here, this is the meridian which passes through the region of Uttar Pradesh, Chhattisgarh, Odisha, and Andhra Pradesh. This is the one which is also which also serves as the standard meridian for India, because it is the time which India follows. So this is what indicates plus 5.5 hours. So that means our time, the time that we experience here, that is 5.5 hours ahead of the Greenwich Meridian time. So here, when we say Indian Standard Time, whenever you hear about Indian Standard Time or IST, we'll study about it in Indian geography as well. But whenever we talk about Indian Standard Time, it talks about Greenwich Meridian Time plus 5.5 hours. So, suppose right now in India, if you assume that the time is 5:30 p.m., what do you think would be the time observed in Greenwich? If India is Greenwich plus 5.5 hours, if right now it is 5:30 p.m. in India, what do you think would be the time in Greenwich? Very good. So if it is 5:30, you subtract 5.5 hours. So if it is 5:30 p.m. in India, suppose, that means GMT would be 12 p.m. So that is how you get an idea about the time as well. But there will come a scenario, for example, if you extrapolate it on the other side, right? Here you observe -1, -2, -3, -4, -5, and so on. So let's consider this one, the one representing -5, suppose. So -5 means what? It means that the time represented there is Greenwich -5, right? So the time of this would be Greenwich GMT -5, isn't it? That would be the time. Means what? Means that if suppose as of now we know that it is 5:30 in India, so it will be 12 p.m. in Greenwich. So what will be the time considered across this meridian, let's say M? What will be the time if you consider that particular meridian? It is -5, GMT -5. So what do you think will be the time? Very beautiful. It will, it will be what? It will be 12 p.m. -5. So that will come out to be around how much? 7 a.m. So when it is 5:30 here, 5:30 p.m., you are experiencing 7 a.m. here, isn't it? Then go to -6, -7, -10. Now suppose I am at -11. -11. Right? Now, if I am at -11 here, that tells me that the time observed here is GMT -11, isn't it? So if it is 12 p.m. it is 5:30 p.m. in India, which makes it 12 p.m. in Greenwich. So what will be the timing observed here? 12 p.m. minus 11. That will come out to be how much? Very good. So timing observed here will be 1 a.m. Now, here is where we start catching the concepts. 1 a.m. So the new day starts when? After 12 midnight. That is when we say that the new day has started, isn't it? So immediately after 12 p.m., that is when the watches they start showing the new day, the clocks they start indicating the new day. So 1 a.m. means that this particular region would have just entered the new day. Now, think about it much more. Suppose I come to here, that is plus 11. Now, this is the region around, let's say, Japan, right? To the east of Japan. So that is plus 11. So if it is 5:30 p.m. in India, which makes it 12 p.m. in Greenwich, so what will be the timing here in Japan at plus 11? What do you think will be the timing? Very good. Plus 11. Greenwich GMT is 12 p.m. So plus 11 means 11 p.m. at night. So here you are experiencing 11 p.m. at night. That means the day is about to end. The day is coming to an end here. A new day is starting. And here, on the other side of the planet, you again have the starting of the new day. It is 1 a.m. Now, do both these places, will they experience the same day? No. When it is sunrise in Japan, it is still the previous day and night time of the previous day in United States. So Japan is ahead in time as compared to United States. So if I have to put this analogy, now that 1 a.m. that you see in the western part of United States, so suppose right now if we are at 5:30 p.m. of 9th of March in India, there you would be celebrating 1 a.m. of how much? And here you have minus 12 as well. So you will be celebrating somewhere around 9th March, right? And beginning of 9th March. So 9th March would be beginning here, right? But what about Japan? Japan would be very soon entering into 10th of March because it is already 11 p.m. there. So in 1 hour, they would be entering into 10th of March. Whereas the region of United States, they have just now entered into 9th of March. So there must be a line which should indicate this change of date. There should be a line. Otherwise, overall, you have a gap of 24, 12 hours almost by the time that you traverse from Greenwich Meridian time all the way till the region of anti-meridian or 180-degree. You have almost 12 hours which pass through. So there must be a line which would separate the areas experiencing the previous day and the one experiencing next day. That line is drawn here. This line that you observe, this is the one which separates, segregates the two different days. Because if you observe on both sides of this line, here you have plus 12, here you have minus 12. That is, if I approach it from here, from the region of Japan, that means in that region, I would be experiencing 12 midnight, and the other part also close to around 12 midnight, but the onset of the new day. So this line which separates the regions experiencing different dates, that is the international date line. It passes very close to the anti-meridian or the 180-degree longitude. It passes very close, but it is not that. It is not the anti-meridian. It merely passes close through that. Now, in this international dateline, you would have observed it is not straight, it is zigzag. Why isn't it straight? When the latitudes, longitudes, everything they are straight, why don't we have the ideal as being straight? That is because in this region of the Pacific, here you have many small different island nations which are there. Now, these island nations, let's say these all these islands make up a nation. Now, if the international date line passes through that or crisscrosses that, that means in the same country, one island will be experiencing 10th of March, another island will be celebrating 9th of March. So that should not happen. One country should at least experience the same date, isn't it? For administrative purposes, for governance purposes, etc. So any particular island, territory, or country, they should lie on the same side of the ideal. So in order to ensure that the ideal does not cut through any country, that is why the ideal is represented by a kind of a zigzag line in order to respect the territorial sovereignty of the countries, so that no country experiences two different dates simultaneously. That is the aspect of international dateline. So the dateline is not straight. Why? The date line runs from the North Pole to the South Pole and marks the divide also between the Eastern and the Western Hemisphere. It is not straight, but zigzags to avoid political and country borders and to not cut some countries in half, so that you have basically the condition that each of the country, they have their, or any of those countries that you consider, they experience the same date at the same time. Now here, when we talk about these international datelines, another aspect that one has to keep in mind, that what happens when we cross the international dateline. So suppose this is your rough ideal. Now here you have the country of Japan. Here on the other side you have the country of United States, isn't it? Japan and United States. Now let me see how many of us know the directions and know the what do we mean by directions or not. So when we talk about the directions, so with respect to IDL, Japan is to the east of IDL or to the west of IDL? What do we think? Okay, most of you are correct, even though many of you are incorrect as well. What is and how do we see the direction? When we are thinking about direction, how do we get to know what is the direction? So the direction is very simple. Whatever lies north, or what is the reference, you take it as north, then you take it as east, west, and south. So if I consider IDL as the reference point, Japan will be to the west of IDL, whereas US will be to the east of IDL, isn't it? Now, what happens if we cross the IDL? Now, here, right now, let's suppose Japan has already started experiencing 10th of March. Whereas United States, that is still experiencing 9th of March. Okay. Now, what happens if you cross the international date line from west to east? Let's suppose, again, the birthday example, let's suppose I have my birthday on 10th of March. Okay. So on 10th of March, after having the morning celebrations and the morning everything about the birthday, thereby I celebrate it in Japan, and then I catch a flight and then I travel across the international date line. Now, in my watches, in my clocks, it is already indicating 10th of March. When I cross the international date line, I reach a location, I reach an area which is still experiencing 9th of March. So if I stay here, I will get to live 10th of March again. And overall, I will get to celebrate my birthday again, because there they are still celebrating 9th of March. I have already experienced some part of 10th of March in Japan, and then I have traveled, isn't it? So in that case, what do you observe? That you have reached a location where it is still being celebrated as 9th of March. So what do you do in your watches? You will subtract a day. Okay, so in the watches, what you will do? You will subtract a day. And overall, what will happen? You will end up living through 10th of March all over again. So in your life overall, you get to live on your birthday again. So you have gained a day, right? So that is what happens when you cross from west to east. And if I basically reverse it, suppose I am crossing from east to west. So when I'm crossing from east to west, when I sat on the airplane, it was 9th of March. So my watch was indicating 9th of March, isn't it? First of all, let me write what we experience when we cross from west to east. West to east. In your life in general, you will get to live 10th of March twice. So you gain a day. And then in your watches, when you cross from west to east, what do you have to do? You'll have to reduce the time by one day, right? From 10th of March, you have to reduce it to 9th of March. So you subtract a day. Subtract a day. Now, if I am crossing the international date line from the other side, that is from United States to Japan. Now, when I boarded the plane, the watch was indicating to me that the date is 9th of March. When I landed, I found out that in that region, people are already experiencing 10th of March, and they have already experienced 9th of March. They have lived through half a day of 10th of March. They are carrying out their daily activities. So in my life, I have lost a day, because I won't get to live the 9th of March and first half of 10th of March ever again. So when you are crossing from east to west, what happens? Lose a day. Okay, you lose a day. Then what adjustment do you have to do with the watches and the clocks that you are wearing? The watches and the clocks that you are wearing, you will have to add it, because it was earlier indicating 9th of March. Now you have reached a location where you are experiencing 10th of March. So in that case, you add a day. So this is what is experienced when you cross through the international date line. And that is how you have to basically adjust your days and your calculator and your watches as well. Those of you who would have read the book Around the World in 80 Days, the fictional novel, which generally is for kids. So if you would have read that, there you will find that incredible usage of this international dateline concept is done. So but nonetheless, those who have not read it, fair enough, don't start picking up that book just because you want to get the ideal clear. Overall, what happens when you cross the dateline? If you cross the international dateline from west to east, then west to east means from the region of Japan to the region of United States, you subtract a day in your clocks. And if you cross the line from east to west, that is the reverse of it, then in that case, you add a day. Okay? This is something which should be understood from a prelims perspective, that kind of an image should be there in your mind with regards to the prelims perspective. Okay? Now, then we come to the systems of Earth. Now, here, when we talk about systems of Earth, this is something that we are going to study, and this is something that UPSC expects you to know. And that is why UPSC has put the portions of geography and environment and ecology that you have to cover. So here you will find that you have the lithosphere. What is this lithosphere? Lithosphere ends up representing all the land that is present underneath us, right? So the land, the water, everything, or not the water exactly, but the land portion, the rocks that you see, the mountains that you see, the interior, the top portion of the planet, or the crust, everything is included in lithosphere. Then hydrosphere, all the water bodies of the planet, that is represented by hydrosphere. Then atmosphere, the air which envelopes the entire planet, which forms a kind of a blanket around the planet, that is what is atmosphere. Then you have cryosphere. What is represented by cryosphere? Cryosphere represents the frozen areas. Frozen areas across ice caps, high mountains, poles, etc. That is what is referred to as the cryosphere. Cryo in general, cryogenic engine is something you would have studied or you would have heard in current affairs when you have the talk of ISRO developing newer engines. You have the cryogenic engine that you would have. So cryo represents anything which is frozen. Okay. And then you have the biosphere, and biosphere basically represents all the living species that you have on the planet, including plants and animals. And that is what you study in the portion of when we talk about environment and ecology. That entire subject deals with this portion. So overall, the coverage of all these areas, or a broader understanding of all these aspects of the systems of the planet, that is something which is essential for you to be able to understand the geographical processes and phenomena, and how life behaves on the planet is something which is understood by that. Now then, we come to the basics of geomorphology, something that we observe in a day-to-day life, something that we experience in our day-to-day lives. So in our day-to-day lives, we always and oftentimes hear about mountains, hills, plateaus, isn't it? Mountains and hills, oftentimes they are used interchangeably. Someone will use the word mountain, other person will use the word hill. Are they same or are they different? Well, they are different. So when we talk about a mountain, this first image that you see, that is what represents a mountain. In fact, the image that you see is that of Mount Everest itself. So here it is the tallest mountain peak in the world. Now here, if you observe few of the specifications or the unique characteristics of this mountain, then you will find it will have a kind of a conical peak-like structure. Observe, this mountain also has a conical peak-like structure. So when we talk about mountain, they have great heights and also conical peak, steep slopes. Okay, generally the mountains, they are classified as the structures which are generally you will find 1,000 meters to 15 meters above sea level. When their height is more than 900 to 1,000 meters, that is something when they are classified as a mountain. Now here, then in the region of the mountains, because they are at such great heights, there water cannot exist in liquid state. There, because the temperature is so low, water basically condenses into ice and snow. So on top of the mountains, that is why you will find the presence and the accumulation of lot of ice and snow. Now in some cases, this ice and that snow that you observe, they start moving down the mountain very slowly. Slowly in the sense, maybe 1 centimeter per month, or even lesser than that. They start slowly and steadily sliding down the mountain slope. Now, after they reach a particular level of height gradient, after they have descended the slope significantly, that is when they start experiencing higher temperature. In general, also, you would have observed when you climb up a mountain or when you go to a hill station, it becomes colder, doesn't it? Why? Because at the top of the mountain, the temperature is very low. So that is where you have at extreme heights, you have everything which is frozen. Now, under the influence of gravity, some of that ice very slowly and steadily that starts falling down. Now, these are large moving ice blocks, but their movement is something which you cannot see with your naked eyes. The movement is so slow that you won't be able to distinguish it with your naked eyes because the movement is 1 centimeter per month or even less. How much is 1 centimeter? This much. This much movement in a month. So for you, it will appear to be almost static, but then very slowly but surely it starts moving down the slope. Eventually, it will hit the bottom. It will come to the lower portion of the mountain, and there the ice and the snow will start melting. And that is what gives rise to the various different river systems in many of the cases. So, this falling or the moving mass of ice down the mountain slopes in general, these are what are referred to as glaciers. These are referred to as glaciers. In many of the rivers across the globe, in many of the large rivers across the globe, not all of them, in many of the large rivers across the globe, this is how the rivers they get their water from. For example, in India, if you consider the rivers such as Ganga, Brahmaputra, Satluj, Indus, all the northern Himalayan rivers that you see, they get their water from this melting of snow. And this is basically brought about by the movement of ice in a very slow manner. That is what we refer to as glaciers. Glaciers will always be associated either with the polar regions or where you have a lot of ice, or with very high mountains where you again have a lot of ice. Then after that, we also have the hills. Okay, we have the hills and the plateaus as well. So when we talk about hills, now look at the hill and look at the mountain. The difference is something which is very apparent. A hill is something which will have a kind of a non conical top. So here, absence of a peak. Absence of conical peak. And here, height is significantly less. Height is significantly less. Okay, that is a hill, right? Many of the times you have the very old or the ancient mountains which are in existence now over a period of time. And this we will, as we will study geography more and more, will come across many of these examples. You'll find that you have instances where earlier there used to exist a mountain in that place. Over a period of time, this has been broken by the natural activities of wind, rainfall, etc. And now they have been reduced to nothing but a small remnant of what they were earlier. So, in many of the cases, the mountains over a period of time they get changed into a smaller version or a smaller remnant of themselves. That is what we refer to as a hill. Okay, so in the case of the hill, obviously no ice formation, obviously no glacial movement, etc. That is something you don't find in the case of the hill. Here you will find in the case of the mountain, you will have generally Or when we talk about glaciers in general, this is movement of mass of ice down the slope. Okay, movement of mass of ice down the slope. Why do they move? Under the influence of gravity. Under the influence of gravity. That is why very slow movement of ice takes place. Not across all the mountains, but in many of the mountains. Then you have what we refer to as plateaus. Plateaus. Plateau is also a term that nowadays is generally used in your English vocabulary as well. That my performance has plateaued, my output has plateaued. So, what is a plateau? Plateau, in simple terms, is a flat tableland like structure. It is a flat tableland like structure. Structure. When we say a flat tableland like structure, what do we mean by that? It means that the structure is similar to somewhat like this. Here, you have slope and steepness on one end, then you will have the flat top, and again a slope to the next. So, this is what is a plateau in general. Observe that the top is almost flattened. So, this is what you have as a plateau. They also have steep slopes. Example, Karnataka Plateau, Chota Nagpur Plateau, Malwa Plateau, Deccan Plateau, Telangana Plateau. You have multiple plateaus in our country as well. So, this is the basic things that you end up seeing or coming across on your day to day lives. Obviously, I am sure I don't need to show you that this is what a river is, this is what a sea is. I hope that much amount of understanding is there. Okay, now here, till now, we have seen the portions with regards to the very basic introduction here. Now we come to the question which had been asked from here in the examination. So this was the question which was asked in examination, that what happens on 21st of June? The sun does not set below the horizon at the Arctic Circle, does not set below the horizon at the Antarctic Circle, shines vertically overhead at noon on the equator, shines vertically overhead on the Tropic of Cancer. So let's see. I'll start a poll. When a land is surrounded in their side, what their side, Nitesh? Good. Most of you have given the correct answer. No, this is not a current affairs based question. This is a very basic concept based question. That what happens on 21st of June? We have seen that 21st of June is the June solstice in the northern hemisphere. We refer to it as the summer solstice. We have looked at it in the previous session, right? This is in northern hemisphere, the summer solstice. So at that point of time, what do you experience? You experience that the North Pole and the region around the Arctic, they experience sunlight throughout those 5 to 6 months. So the sun does not set in that region. So that is where the answer will be very much A, right? Okay. When you have water surrounding the land on three sides, that is a peninsula. That is what is referred to as a peninsula. Okay. Now, then we come to the portion of the second module where we talk about the formation of planet Earth. Now, here in this portion, we talk about the planet Earth, its interior, rocks, and also the various theories which are required for geomorphology. This is where we actually start the coverage of the syllabus, which will be very important for your examination. Now, in this portion, this is an area which is relevant for you both for your prelims as well as for your mains. So, this is something where in the prelims, you get questions with regards to structure and interior of Earth, structure and interior of Earth. Then after that in prelims, presence of elements, elements in the interior. Then after that, the portion of rock types and their basic properties. And then plate tectonics and also associated phenomena. Okay, that is something which you will find to be relevant for the prelims examination from this module. And for the mains examination, the portion with regards to rock type sometimes, then continental drift theory, then plate tectonic theory, or rather, before that, seafloor spreading theory, then after that, plate tectonic theory, okay, types of plate tectonics or types of plate movement. That is something which is going to be relevant and important for your mains examination. So you have the portions which are going to be relevant from this module for the prelims, and also the portions which are going to be important and relevant for your mains. Moreover, please understand that this module will form your basic concept. And if this is in place, then understanding the formation of mountains in a region, or the movement of continents as we experience, or occurrence of earthquakes in various parts of the world, or occurrence of volcanic eruptions, in which areas of the globe do we experience volcanic eruptions, everything will be clarified very simply if you have an understanding of the basic concept of this module. That is how important this module is. Once you understand this, then you won't find much difficulty, and you won't be forgetting it very soon as well, provided that you are not simply staring at the screen, provided that something is going inside as well. If you only ensure that much, This is going to be a very fruitful module for you for the examination as well. And trust me, in the prelims or in the mains, you don't want to get the questions appearing from this as incorrect, because this is one of those areas where your competition will step out and hit a major sixer, because the type of questions that you get from here are very direct, right? So that is something where your competition, at least those who will clear the exam, and if you are considering your competition as your neighbor and both of you don't qualify for the exam, then it is a different matter altogether. But if you are competing with someone who is clearing the exam, they will never commit any kind of mistake in these type of simple topics. So that is where pay maximum attention to this, try to understand this, what it is, and then if you take a look at the rest of geomorphology, it will be a much easier task for all of you. Okay, right? Okay, plate. Preetham, see, as of now, my dear friend, we have not studied about plates. So if I start defining what the plates are, for that you need to understand what lithosphere is. For that you need to understand what the structure of the planet is. For that you need to understand what the interior of the planet is. Isn't it? Please trust the process. I will not leave you high and dry where you don't have any clue what the plates is, and I tell you that you will expect a question from here. We will cover all of this. Let's go chronologically, the portions that we have studied. If you have issues in that, then ask a question. Associated phenomena, we'll talk about it. Yuvraj, why are we not going through book? Which book, Yuvraj? If that would have been the case, then you need the book only. Why do you need the live class? If you need someone who will narrate you the book, all you need is an audio ebook where you plug in your earphones and they will tell you, recount the entire book. They will read through each of the sentence. You Why do you attend the live session? To extract something extra which might not be there in the book, isn't it? Please try to distinguish yourself from the mode of preparation or the mode of studies that you carried out till class 6th or 7th. Please try to do that. Okay. And sea and ocean difference. Sea and ocean. See, oceans are very large water bodies generally, and the seas are, they are shallower than them, they have less amount of depth, and they are at the margins of the larger oceans. They are along the coastal areas of the larger oceans. Okay. Gauri, which calculation? Till now we have not done any calculation here, my dear friend. Where have you found the calculation? Akansha, kindly look at the annotations of the PPT. Kindly look at the previous module as well, the first session's module. There we have explicitly written in the slide as well that what happens in the Arctic Circle on 21st of June, what happens on the Antarctic Circle on 21st of December, what happens on equinoxes. We have mentioned it very elaborately. Kindly go through that. Even after that, if you are unable to understand, write to us, then we will help you out. Okay. Chilika Lake, the name in itself has a lake. It is a very smaller water body. Seas are very large water bodies. Okay. See, if you have to think about it, if you have to understand the meaning of it, please, for the last time, I'm repeating it, try to understand it. Otherwise, please don't think about it that UPSC is going to ask you to this level. Why is Chilika not a lake? And why is the lake beside my house? Why is that not called an ocean? Indian Ocean, Pacific Ocean, Atlantic Ocean. But what about my backyard pond? I will call that my own ocean, Bangalore Ocean. So why? Understand the simple process and the simple aspect of it. There is no one authority who will issue the definition every year that this is the definition of the ocean, this is the definition of the sea, mug it up, vomit it out. So please understand it. Oceans, when we talk about hydrosphere, hydrosphere talks about or consists of water bodies. Now, the water bodies which are present across the planet, few of them, they have a great depth. And the depth and the expanse of it is so huge that the average depth to the bottom from the sea level is around 4 to 5 kilometers from the surface. And they have a large area where light never penetrates. So it is permanently dark. Now, these large water bodies, when we talk about the coastal areas, for example, consider the case of Indian Ocean and compare it with the region of Indian coastline. Now, when you come to the Indian coastline, the water is slightly shallower, right? It is not as deep as you get into the middle of the Indian Ocean. Water is a bit shallower, but nonetheless, there also you have a lot of water, and it is closer to the coastal region, coastal land. And because it has got shallower water, the type of life that you will find there, the type of geological properties that you will find there, everything will be that ascribable to a shallower water body as compared to a deep water body. So that is why the type of life that you find in the sea is different, the temperature experienced in the sea is different. In the case of the ocean, the depth is different. So these are minor differences which exist. Okay, right? I hope this is understood. Okay, can we proceed now in this portion? Good. So we start with the basics with regards to the formation of Earth. How is it that the planet came into existence? We have talked about the origin or the genesis of the entire universe. How is it that the planet came into existence? We do know that in our solar system we have one star, and that star is the sun, isn't it? So the sun in itself came into existence roughly around 5 to 4.5 billion years ago. So sun overall, if you will observe, sun came into existence around 4.5 to 5 billion years ago. Now sun is a star, which means that sun produces lot of heat, lot of temperature, and provides light as well. Now, in the initial days when the solar system came into existence, at that point of time, you did not have lot of planets which were around. You had the remnants which were left behind as the star was born, as the star was created, and as the star came into existence, you had the remnants of the dust particles surrounding the sun. So that is what the very initial solar system looked like. The very initial solar system, if you will observe, this suppose I assume as the sun. Now all around the sun, you had a large area in the entire present day solar system where you have all the various different planets that you see right now. In that entire region, you had nothing but a lot of dust particles which would move around the sun aided by the gravitational pull of attraction. So you had a gravitational pull of attraction, and that is where you had all these dust particles which would be moving around the sun. Okay. They would be consistently moving around the sun. And this is just a small band I have indicated. Like this, you had the entire solar system almost covered. Now, the dust particles which were present right next to the sun, they were sucked in by the huge gravitational pull of attraction and the very high temperature which was present around the sun. So that is why in the immediate vicinity, there was a clearing and nothing was present in the immediate vicinity because everything was sucked in by the sun and everything was used up by the sun. Then, as you slightly started moving farther away, you had a lot of these dust particles, and all of these dust particles, they were consistently in motion, they were consistently in movement. Now, with mass comes a physical property of gravitation. I hope we are aware, and we talked about it in the first session as well. Any object, any body which has got mass, that body will have its own gravitational pull of attraction as well. Suppose if I consider two objects, suppose I consider this pen and this pen holder. Now, this pen holder that you see, this is heavier as compared to this pen. So, the gravitational pull which will be extended will be greater by this pen holder as compared to this pen. So, greater the mass, greater is the gravitational pull of attraction experienced. Remember this. Greater the mass of the object, greater is the gravitational pull of attraction. Always. That is why you would have heard about this, or you would have at least seen the videos, right? When you see Neil Armstrong walking through the moon, you will observe basically that it is a kind of a jump, right? The astronauts, they are able to jump on the moon surface. Why? Because moon's gravitational force is less. Moon's gravitational force of attraction is much less as compared to Earth. Why? Because moon is lighter as compared to the Earth. So anything which has got mass will have a greater gravitational pull. Now, once we have understood this, suppose, yes, here this is the sun. Now, suppose you consider these dust particles, all these dust particles, they are moving in random motion. Now, collisions, they started taking place. Collisions between whom? Collisions in between these dust particles. That started taking place. Now, when you had collisions which were initiated, what was the result? So, basically, when collision happens, there can be certain consequences. Suppose two objects, they come in and they crash with each other. It will be further broken down into smaller pieces, smaller particles. It will be further spread apart, right? That is also a collision. But imagine a collision where an object is moving in this direction. Another object comes with a speed and then collides. In that case, there will be collision, but the objects or the materials will not split, will not break into different pieces. So, like this, the dust particles, they started colliding with each other. Now, when the collisions happened, whenever collision happens between any objects, any solid object, you will observe there is heat which is produced. If you have to understand an analogy of this property of physics, do one thing, ask someone to offer their cheeks or offer your own cheeks. If you are very Gandhian in your approach, offer your own cheeks to someone that slap me. And when they will slap you, feel the temperature of your cheeks, it will rise up. Feel the temperature of the palms of the hand as well, that also rises up. So that tells you what? Collision of solid objects leads to heat being produced. Same is the case with the various particles as well. So collision always leads to production of heat. Because by clapping, many of the times the essence of that experiment gets lost. It is with a slap that the mind opens up. So collision always produces heat. Now understand what happened across our solar system around 4.5 billion years back. Now I'll try to recount it as a story so that later on it is easier for you to place it in a kind of a chronology, right? So listen to this very carefully as of now. So initially what used to happen was you had many of these dust particles. Now all these dust particles were consistently moving around the sun. Now the dust particles, they started colliding with each other. Now with each collision, you had significant amount of heat which was produced, lot of heat. And due to that heat which was produced, at the point of contact, the materials, they started getting welded together because there was so much of heat. Everything in that localized region, they started melting, vaporizing, and eventually the materials, they started bonding together or welding together. So with each collision, the size of the particles, they started to rise, they started to increase. Okay, let us write it down. So with each collision, with each collision, the size increased and more heat was produced. Okay, now with each collision, now as the size increased, what would happen to the gravitational force of attraction? We know that greater the mass, greater is the gravitational pull of attraction as well. So, because the size was increasing with each collision, that meant you had a greater gravitational pull associated with it. Greater gravitational pull. And greater gravitational pull would mean what? It would attract more particles around it. So that would result in more collisions. More collisions, right? Because it would attract more particles. So initially, what started with dust particles colliding with each other, so when the dust particles would collide, the region would be melted and it would form one larger cumulative or accumulated mass. So with each collision, the size would keep on increasing, and with an increasing size, you would have more gravitational pull, means that a particular large mass would attract more particles and more collision would take place. This led to the formation of few of the very large structures, and that is what we refer to as planetesimals. So this led to formation of planetesimals. Led to the formation of planetesimals. Now, these were large masses, not as big as a planet, obviously, but significantly larger. So they gained a certain momentum, they had a certain velocity associated, and it was because of these collisions. Suppose an object is going like this and a collision happens here, then another collision happens here. So, like that, multiple collisions that induced a kind of a spin as well in these planetesimals. So, that is how, in the initial days, the spin was introduced in the case of these planetesimals. These were not rounded or spherical in shape. They had a very kind of an irregular shape, as is estimated. And still, they would have a kind of a spin around their central object or the central point. And that is where these planetesimals, they were very well en route to create another massive collision. and collision of these planetesimals that led to creation of planet. Collisions of planetesimal led to formation of planets. So planetesimals are nothing but building blocks of planets. Building blocks of planets. Okay. So like this, you had multiple collisions, hundreds, thousands, millions, billions, and trillions of collisions happening on a daily, hourly, and minute by minute basis. Like this, multiple collisions which happened all across the solar system that led to all the dust particles which were present, all of them were consumed, and eventually you were left behind with 8 different planetary systems. That is, you had the different planets in existence, whereas the rest of them, they were consumed in these collisions. That is why nowadays you don't observe these collisions anymore. You would observe these collisions in the initial stage of the or in the initial phase of the solar system, when the solar system was very unstable. So all these, they kept on moving, colliding with each other for hundreds, thousands, and millions of years. And that is how, after around 500 million years, 500 million years, if you have to think about it, if sometimes you hear 500 million years, it doesn't give you the exact amount of idea. So 500 million years is, in terms of crores, if you convert it, you get an idea. It is close to around how much? How many crore years? Think about it, and then then write about it. So basically, that is for how long that these collisions, they kept on happening. They kept on happening around the sun. Now, with each collision, because you had solid particles and solid objects colliding with each other, with each collision, you had a subsequent heat which was produced. And that heat which was produced, that would melt the surrounding portions as well. Eventually, when you had all these hundreds, thousands, millions, and billions, and trillions of collisions happening, so the planet which was created, obviously, heat would be very high. So, around 4.5 billion years ago, what was created was a liquid ball of mass. So, here you had a liquid ball of mass. This was 4.5 billion years ago. Okay. Prithvi, that is why I always say listen to the entire thing very carefully. See, your question is collision should have created breaking apart and reduce the size. That is why in the initial portion I already told you that if the collision happens head on, things get broken apart, they disintegrate, and they get broken into smaller parts. But if an object is moving like this and in the same direction, if there is a collision which happens, then the fragmentation does not happen, accumulation results along with the heat. That is why you have things accumulating together. This theory is contradictory in reference to Big Bang theory? Absolutely not. Suraj. Why sun is unable to attract those dust particles? Sun is attracting those. That is why it is moving around the sun. Anything which is moving around the sun is because sun is attracting that. Why do you think planet Earth is rotating around the sun? Is it because God designed it that way, that you shall rotate around the sun endlessly till someone asks this question in UPSC exam? Is it like that? No, because of the sun trying to pull Earth to itself. That is why it continues in rotation. Remember, in the first session, we talked about the aspect of why anything rotates in the case of satellites, in the case of planets. The same logic here. Yes, Abhishek, very correct. Shamil, no, this is not the interstellar dust hypothesis. This is the accumulation theory of planetesimals. Okay. Does any form of introduce, say, there are theories with regards to the introduction of the other stars, etc., but please don't listen to all of that. Nitesh, sir, every planet is made out of collision. So if every planet is made out of collision, does that mean all of the planets will be constituted or composed of the same particles? Where does that idea come from? That if, for example, that if any particular process for production is used, let's say cars are produced in a factory, and I say milk is also packaged in a factory, so car and milk should be the same because both are coming out of factory. So if the planets are forming as a result of collision, does that mean that all the planets will be the same, Nitesh? No, because in all of the cases, you have different particles which were involved, different elements which were involved, different number of collisions which happened, the duration after which the collisions happened, all of them was different, isn't it? Why the particles didn't got stuck to sun itself due to gravity? Okay, so this happened last time as well. Yashika, I'll ask you the question again. Last time I asked you a question, you disappeared after putting your question. So I ask you the question again. Why is it that the earth moves around the sun? What is the force which is responsible for the earth moving around the sun? Let me know. It is because of gravity, right? Gravitational pull. Please don't write centrifugal, centripetal forces. Centripetal force never acts on a body independently. It is acting only on a moving object. It is the gravitational pull of attraction which acts. Now, here also, when we talk about here, in the case of the formation of the dust particles, in the initial stages, again, I have told you that immediately surrounding the sun, all the small particles which were there, all of them were taken in, were sucked in by the sun. So, immediate vicinity which was there, that was sucked in. But then you had few things which were, let's say, 50 million kilometers away and more. So, there you had the implicate gravitational force which was acting. And many of them had a kind of slow motion, a kind of a collision, etc., and collision induced motion, due to which they are trying to fall on the sun. That is how the planet also moves. So they try to fall on the sun, but because they have a velocity associated, that is why they end up revolving around the sun. Can the collision happen today? As I told you already, that basically in the unstable form of the solar system, when the solar system was not very stable, at that point of time, you had many of these particles which were present. So you had millions and billions of collisions happening on a daily basis. But that is where in the entire process, all these particles were consumed into the formation of the planets. That is why in the case of the planets, we don't observe these collisions to be happening every day. Okay, right? I hope that is clear. Darshan, sir, you have spoken about two types of consequences in collisions. Please repeat it for the last time. Darshan, what if someone else asks me about the same after you? That last time. Please pay attention. I have already repeated it 3 times. This is the last time I am saying. I'm not going to repeat this because, see, It's okay for me to spend 24 sessions only on the structure of planet Earth, but it is not okay for your preparation aspect. So I can be on this topic, I can drive a lecture for 24 hours only on the formation of the Earth if you want. I'll be very comfortable in that. It is up to you to choose. So here, basically, when we say that there are multiple types of collisions, suppose when we have two particles which move against each other with a significant amount of force, then they will break or they will get fragmented into multiple smaller pieces. But if suppose both of them are moving in the same direction, thereby there will be a collision which will lead to an accumulation rather than a fragmentation. If one is moving in a direction, another one is moving in the same direction, it will add some momentum, it will add some velocity, and in many of the cases, due to the heat produced at the point of collision, the two materials will get together to form a larger material as well. Okay. This liquid ball of mass that we are seeing, this is what we refer to as Earth. Okay. Yes, like frictional welding. Planetesimal building blocks of planets, the smaller versions which collided to form the larger planets. So again, I will repeat the entire process till now. So immediately after the formation of the sun was the one which consumed all the gases around it, and it produced energy as a result of that. Now, in the solar system at that point of time, in the place that we see planets as of now, you did not have the existence of planets. But in place of these planets, you had the existence of a lot of various kinds of dust particles which were present. Now, all these dust particles, they were moving around the sun due to the gravitational pull of attraction of the sun. They would be moving around the sun. Now, as they would be moving in a certain direction, thereby they would undergo collisions amongst themselves. Collisions amongst whom? Amongst the dust particles themselves. Now, as the dust particles they would collide, with collision of any two solid objects, there is always a heat produced. So, when the dust particles would collide, there would be heat which would be produced. And due to the production of that heat, the temperature of that material, of that particle, would start rising, right? And also you had dust particles which would accumulate because so much heat was produced that there would be a natural welding process which would be resulted out of it. So slowly and steadily, more particles. So suppose a particle is moving very slowly and independently, that today is my day, let us explore the solar system. Somebody comes and hits this particle. Now that particle will gain a momentum and it might strike the third particle. That will gain a momentum, it might lead to the fourth collision. So, like this, you had multiple different cascading collisions which were experienced. Then, when you did have these many collisions taking place, simultaneously every collision would lead to production of heat. So that production of heat would heat up or warm up the entire particle. Slowly and steadily, you had multiple of these collisions taking place, and eventually you had the formation of a large planet shaped object and planet sized object due to these collisions. But every day, because hundreds, millions, thousands, billions of collisions would take place, so every day you had more heat which would be produced. And due to that heat, initially the planet which got created around 4.5 billion years back, it was nothing but a liquid molten ball of mass. And liquid molten ball of mass, which was comprised of many different elements were present, many different compounds were present because of all the various different types of elements which could come for that collision. So that is why you had a diversity of the elements which would be present. Now, this is something that you had around 4.5 billion years ago. Now, what happened in between these 4.5 billion years that we see the planet that today we call as the blue planet? So, something might have changed. In fact, a lot of it changed. Let us understand how. In the initial days, everything was liquid. And when we say liquid, it was not the same kind of element. It had different elements. It had presence of some calcium, silica, aluminium, magnesium, nickel, iron. You had different types of elements which were present in the initial planet. Now, before we proceed on, a very basic experiment. So suppose I have a jar here, right? And I take three liquids, and I pour those three liquids. Which three liquids? I take honey, I take water, and I take oil. Now, when I pour these three liquids, or when these three liquids would be present in the jar, would they mix very easily, or would they be placed in layers? What do you think? When I pour these three liquids, would the liquids separate themselves into layers based upon lightness or heaviness, or would they be mixed perfectly together? Very good. They would be placed in layers. In general, what do you observe? Which will be at the top and which will be at the bottom? Under general circumstances, you will observe that the honey that you see, that will sink at the bottom. Then you will have water. And then you will have the thin film of oil, which will be floating at the top, right? So I think this is a kind of an experiment that you can do at your house as well. And nonetheless, you would be very familiar with the outcome of this experiment. Now, here, when we think about it, the planet 4.5 billion years ago was in a state which was very similar to this. It was molten, it was nothing but liquid. At that point of time, it was nothing but a complete liquid. Liquid composed of various different types of liquid. Liquid of iron will be different from liquid of nickel. Liquid of silica will be very different from liquid of aluminium. Liquid of aluminium will be very different from liquid of magnesium. But you had these liquid. Now, what would happen when you have all these liquids mixed? So, the heaviest one will sink to the bottom, isn't it? The heaviest one will always sink to the bottom, like in the case of the jar or the beaker. So, here, the heaviest one, the heaviest elements, they started sinking to the bottom. They started sinking to the bottom. I hope the bottom portion is clear. I hope nobody is of the opinion that this forms the bottom of the planet. I hope everyone is aware that if you start digging into the planet from wherever you are in the planet, it is not as if you will emerge out of Antarctica. You will emerge at the center of the earth. So, center is the bottom of the planet. I hope that much is clear. Now, so the heavier elements from all sides, they would sink to the bottom. Okay, so heaviest elements would sink to the bottom. Now, at that point of time, if you consider which were the heaviest elements which were present at that point of time when you consider the planet, so you had the presence of iron and nickel, which were the heaviest elements of that time. Iron and nickel. So these settled at the bottom of the planet. These settled at the bottom of the planet. And that is what led to the formation of core. Still today, the core that you find, that is something which has got the presence of both iron and nickel. Now here, slowly and steadily, the number of collisions reduced. Now, when the collisions would reduce, at that point of time, what would happen? Slowly and steadily, the cooling process would happen. The cooling process would be initiated, isn't it? However, as the planet was slowly cooling down, it was still very much in liquid state. But then at that point of time, you had a very giant final collision where a very large, almost to the size of Mars, that large object collided with the planet. Now, when that large collision happened, significant portion of the planet that was separated. But then it could not go very far away because the Earth's gravitational pull kept it or held it very close to each other. And that object which got, or that portion of planet which got separated from the Earth and which was held by the planet due to the gravitation, that is something which we still see today almost on a daily basis. And that is what constitutes our moon. So the moon that we see, that moon was also created as a result of one of these collisions which took place. Okay? Nonetheless, when you had these collisions, eventually there is something that you observe when there is a cooling of liquid. If ever you have observed how the liquid cools down, for example, if you heat up a utensil full of milk, now it starts boiling and bubbling. But when you switch off the gas, after some time you will find that the top of that milk, that develops a kind of a wrinkly layer, and that is cooler. But if you dip your finger underneath, the liquid is still hot. So that tells you that cooling always is initiated from the outside, from the exterior. That is how always cooling is initiated. So here again, cooling was initiated from the outside. Okay, so cooling was initiated from outside. Now, as cooling was initiated from outside, obviously the materials would not cool down in a perfect sphere. You would have some areas which develop some kind of wrinkles, so to say, right? Their kind of creatures would develop. In certain areas there would be, because the outside material in itself is contracting, so in certain areas it would contract more, creating depressions. In certain areas it would contract less, creating ridges. So the contraction of the surface, that produced irregularities on the surface in the form of very deep valleys, large deeper areas, and few upfolded regions as well. But then, in the inside, materials were still molting hot. They were very, very hot. Now, amongst these molten materials, you also had the presence of certain gases. How? When we say everything is in molten form, where did the gases come into existence? So, for example, suppose, let's say I consider silica. What is the formula of silica? SiO2. Now, if I, let's say, melt it up, I heat it up so significantly that it melts. What will happen? While the Si, that is the silica, that will get molten, but what about oxygen? Silica otherwise is solid, but if you melt it up, what will happen to that oxygen? That oxygen will escape as a gas, isn't it? Similarly, think about ferric oxide, right? That you see, suppose Fe2O3 or Fe3O4, all these iron oxides. Now, ideally, they are present in solid state. Right now, if you want to go out there and get some iron oxide, it will be present in solid state. But what if I melt it? The iron will get converted into molten liquid, but what about the oxygen? The oxygen shall always be released as a gas, isn't it? So that is what you observe whenever you have any of these compounds which are melted. So because of this, in the interior as well, you had the presence of lots of gases. Okay, so in the interior, gases at high temperature were trapped. Again, I will repeat, how is it that you had the presence of gases in the interior? Ideally, because that is a question which is very natural to erupt in your mind, that right now you were saying that everything is liquid. Now you are saying, by the way, there is a gas as well. First of all, you become clear and then you teach to us. So it is very natural for you to have this doubt. But then think about it. You had various different elements which were present and which were continuing these collisions. Now, all these elements does not mean they were pure nickel, pure cobalt, pure chromium, or pure sodium like that. No, they were present in the form of various compounds. Now, for example, if let's say you consider calcium carbonate, CaCO3. Now, calcium carbonate is a solid, isn't it? But then if you heat it up significantly, only this calcium will be molten. What about CO3? It will get converted into carbon dioxide and oxygen will be released, isn't it? So, if I'm melting CaCO3 somewhere here, basically all I get is molten calcium, and along with it, I will have bubbles of oxygen, carbon dioxide, etc., which will be present. So, like that, because you had so many different compounds which were present, all those compounds, when they were molten, all of them, wherever gaseous molecules were present, they continued to be heated up and gases were present. Now, all these gases, when you have a lot of gases which are trapped, what do the gases try to do? Because they are lighter, always gas is going to be lighter, right? So because they are lighter, they will tend to rise up, isn't it? So all the gases they were at high temperature were trapped, try to rise up. From every place the gases would try to rise up, they would try to move closer to the surface. Now that led to a scenario where all these gases, they would erupt significantly, because by that point of time the surface that you are standing off as of now, that was not the surface at that point of time. In fact, right now we do know that the oxygen is present in atmosphere. At that point of time, our atmosphere did not consist of oxygen at all. At that point of time, our atmosphere had only the presence of hydrogen and helium, right? So we will study in the portion of climatology as well that how the current atmosphere that we see, how that has come into existence. But that was the condition, and the surface was still getting formed, it was still cooling down, so it was still weaker. Surface was weaker. In the interior you have a lot of gases which are trapped. What will be the resultant of it? The gases will try to escape, and thereby you had volcanic eruptions. Volcanic eruptions. Now, through these volcanic eruptions, which would basically number into hundreds, millions, thousands of millions, and billions of eruptions on a daily basis happening across the planet. Across the planet, numerous eruptions were happening, and they were happening simultaneously in many of the cases. Why? Because the gases wanted to escape. this is where you had so many volcanic eruptions and so many gases which were released. Generally, gases such as ammonia, NH3, gases such as carbon dioxide, gases such as methane, gases such as sulfur dioxide, these were released. And also, another very important gas was released, and that was hydrogen along with oxygen, which was released. They combined at this stage of time to form the water vapor molecules. So, in this phase, along with the gases, you had hydrogen and oxygen combined to form water vapor. So, this is the phase of formation of the planet where the gases primarily wanted to escape. And that is why this phase of the formation of the planet is also what is referred to as phase of degasification. Phase of degasification. Now, this water vapor was released along with the other gases. Now, all this water vapor that led to the formation of clouds. And all these clouds, basically, they surrounded the entire planet. All these water vapor eventually led to the formation of the clouds, and basically, all these clouds, they surrounded the planet. You had all the clouds surrounding the planet. Now, when the clouds did surround the planet, they successfully managed to block the sunlight. You had the clouds. And what they did was they blocked the sunlight. And what happened when sunlight was blocked? The rate of cooling was further increased. So, more cooling took place. Now, you had more cooling which took place, as a result of which you had more condensation of water vapor into clouds, and that led to a phase of torrential rainfall. Torrential basically means a kind of an endless phenomena. So that led to a phase of torrential rainfall where it is estimated that it did rain continuously on the planet for a duration of close to around 8,000 to 9,000 years. For that duration, it continued to rain throughout the planet. Imagine a rainfall which initiates or which was initiated, imagine, during the Indus Valley civilization or the Harappan civilization, and it continues to rain even till today and for more 4,000 years. So that is how long the rainfall continued. So that was the phase of torrential rainfall. Torrential rain, where it did rainfall for 7,000 to 8,000 years. That is when the planet got the existence of all the various oceans, the seas that you see around us. That is when they came into existence. In the initial stage, you had nothing but water bodies which surrounded the entire planet. And that is how, from the collision of the dust particles, we had the emergence and the creation of what we today refer to as the blue planet. Okay, so in very brief, initially you had particles undergoing collisions, right? Slowly and steadily, the mass increased, led to the liquid ball of mass getting created. That liquid ball of mass which was created, that was consisting of various different elements. The heaviest of those elements, they settled at the bottom. They formed the core. Which were those heaviest elements? Iron and nickel. They formed the core. Okay. Then the rest of them, that started cooling down, and cooling down process, it was initiated or begun from the outside. That is when the outside surface started cooling down, creating ridges, crevices, uphill portions, etc., irregularities. Now, in the interior, you also had the presence of many gases which were still trapped. Now, these gases, they tried to escape, and they escaped because the surface was still not very hard enough. So all these gases, they brought along with them various different molten materials which were present, and that led to multiple volcanic eruptions. All these volcanic eruptions led to the elimination of gases from the interior. Now, amongst these gases, you had the presence of methane, carbon dioxide, ammonia, and so on. Along with that, you also had water vapor. Now, that water vapor led to the formation of clouds. Those clouds blanketed the entire planet. That blanket, in a way, shielded the planet from sunlight, led to further accelerated rate of cooling, meant more water vapor condensed into clouds, and led to a continuous rainfall. Now, that rainfall, that is something which is said to have continued for 8,000, 7,000 years, and that is what filled up the water bodies or created the hydrosphere that we see around us. And this further accelerated the rate of cooling, because more rainfall meant greater rate of cooling. And that is how slowly and steadily, roughly around 4 billion years back, or around 3.8 billion years back, that is when the planet started gaining a kind of a stability. The genesis of life on the planet, that happened around 3.5 billion years ago, in these water bodies, in these oceans, with the blue green, or the cyanobacterium, as it is predicted, that these were the chemotrophs. They utilized the chemicals. These were unicellular organisms which would utilize the chemical nutrient present around them to produce food. So that is how the entire process of formation of planet, that is something which took place. Okay. Moon was created at the phase when you had this phase, when it was still very much in liquid. At that point, you had a very giant mass, almost to the size of Mars, that collided with the planet. Significantly, some portion, some chunk of the planet was separated, the liquid form, but it could not move very far away because the Earth's gravitational pull was so significant. So that portion which was separated, that also cooled down, continued to be held by the Earth's gravitational pull, and that is what we refer to as the moon. Okay, right. Now, after this, let's take a break. Okay, so we'll take a break and we will be back after 10 12 minutes. So we'll be back by 7. So let's take a break till 7. Okay. Sarthak will study about it when we come to atmosphere, why nitrogen is still present more in the air but not on the surface. On the soil, you don't have nitrogen, but in air, you have plenty. Why? We'll study about it, all these. Okay, let's take a break and we come back. A confirmation regarding the audio, please. If you're able to hear me out perfectly well, kindly confirm. Thank you. So, this is how we had the formation of planet Earth. Now, mankind has always wondered what the Earth is made up of. Initially, we did not have the adequate amount of science and technical information and knowledge around us to even know the dimension of the planet. It was only much later that we got to know how large actually the planet is. And in the initial stages, there was a lot of discussion, a lot of debate about the fact that whether the planet is flat or whether the planet is round. You also had a lot of flat earthers, as they were referred to, because they thought that the planet Earth is flat, that if you keep on sailing from one part of the earth to the other, eventually you will fall off the edge. That is what they thought about. Later on, it was understood that no, planet Earth is not flat, it is nothing but a spherical object. But it is not a perfect sphere either. The shape of the planet Earth is what is also referred to as a geoid. Geoid. What do we mean by a geoid? So it is the shape which is very much peculiar to planet Earth itself. And in this shape, you will find that it is slightly flattened at the poles and slightly extended or bulged around the region of equator. That is the kind of shape that we have in the case of planet Earth. That is why it is referred to as a geoid. Now, what constitutes the interior of the planet? So, when we talk about the interior of Earth, so our understanding or our knowledge about what constitutes the interior, that has increased drastically and tremendously in the past 100 or 150 years. Before that, we did not had much of an information about what really constitutes the interior. So how is it that we came to that conclusion that, okay, if in the interior some portion is molten, why is it so? Or is there a portion which is in solid? How do we get to know about that? So basically, when we talk about the interior of the earth, we have our own sources of information. Sources of information. Now, these sources of information can be divided into two parts. You have the direct sources. Direct sources. Direct sources are the ones which give you a direct insight into what is present in the interior. They give you the first hand information. For example, the volcanic eruption. Volcanic eruption. For example, mining and digging. Mining and excavation. So all these give you a direct information regarding what is present in the interior of the planet. These are the first source. For example, in any particular region, let's suppose there is a volcanic eruption which occurs. As soon as there is an eruption of a volcano, immediately in that eruption you have materials from the inside which are thrown on the outside, which are thrown and spread on the exterior, isn't it? So that is where also you get an idea about what is present in the interior. Sometimes when you are carrying out the digging and the mining processes, excavation processes, there also what do? You dig up so deep so that you get an idea and an information that what is the material which is present in the inside. But there's a kind of a limitation here, and the limitation is very stark and very significant at the same time. When we say limitations to this, what do we mean by that? So for example, when we say mining and excavation, the deepest mine which is present across the planet, that mine is present in the northern part of Eurasia, that is the Europe and the Asian continent. And there in the Kola Peninsula, there you have the deepest mine, which has a depth of few kilometers. It is said to have a depth of around 10 kilometers. But there also, that mine was abandoned very quickly, because by the time that people would reach to around the depth of 10 kilometers, the temperatures would start rising to a very uncomfortable level. Many people would die. So that is why even that mine was abandoned. So think about it. Our study about the interior, that is restricted to the height of, or to the depth of, only 10 kilometers. In the case of a planet which has got a radius of 6,400 kilometers, so how is it that we are supposed to know about the rest of the planet? That is where we take use of indirect sources. Indirect sources of information. Now, which are these and what are these indirect sources of information? So, in the case of the indirect sources of information, you have seismic activities, seismic activities means earthquakes which are generated. We'll study about the seismic waves later on, that what do we mean when we have an earthquake, how are the waves generated. That is also something which gives us an idea about what is constituted in the interior. When we study about these waves or the earthquakes in detail, we'll get to know about it. But as of now, just be aware that these earthquakes, when they occur, they generate energy waves, and those energy waves, they travel through the interior of the earth, and they give us an idea about what constitutes the interior structure of this planet. Then, other than that, you also have magnetic and gravitational anomalies. Anomalies exhibited by the planet. Now, this magnetic force, or the magnetic field exerted by planet Earth, is because of what? It is because of the iron and nickel which is present in predominant quantities in the region of the core. So it is that iron and nickel that you find in the region of the core, that is the one which generates these magnetic fields, right? So by studying of these magnetic fields, we get an understanding that, okay, yes, this kind of materials must be present in the inside. That is why we have these magnetic anomalies. In case there is any shift which is observed in the magnetic poles, there also we get an idea, okay, there must be certain changes happening in the interior. That is why these are the changes which are visible to us. Now, other than that, you also have asteroids, meteors, etc. Now, all these small objects which keep on moving in the solar system, that is the asteroids, for example. For example, as you would know that in between Mars and Jupiter, you have the very large asteroid belt where you have hundreds and millions of asteroids continuously moving around, isn't it? So you have those asteroid belts which are present. Now, what are these asteroids? What are these meteors? These are basically the remnants of the solar system that we had talked about. The unstable solar system, where you had a lot of debris, lot of dust particles, all of them collided to form the planets. You still had certain remnants which were left behind, and those were the asteroids and meteors that we see today. So by studying these asteroids and meteors, we get an idea that what the early solar system would have looked like, what the materials would have looked like, the materials which eventually collided and led to the formation of the planet, what would they have looked like? So that is why you will find that there is an increased international effort in order to study and understand these asteroids, in order to understand the mineral distribution in these asteroids. Why? So that we get to know that, okay, if this was the mineral distribution, so that would also have been the case 4.5 billion years ago when the planet would be formed. So that gives us an insight into the past history of the formation of the planet. So it is with the help of these direct and indirect sources by which we get to understand that what the interior is constituted of. Now, for a long period of time, our understanding was absolutely limited, as we have mentioned, because of lack of technology. In the 1900s, when the earthquakes they started being observed and recorded, and you had the study of the seismic waves or the energy waves generated from the earthquake, then suddenly and rapidly our understanding about the interior that started increasing manifold. Overall, you can broadly classify the interior of the planet into three broad structures. What structures? So you have the outer layer, which is referred to as the crust. It is the thinnest layer which is present. Okay, that is the crust. So, crust, think about it. If let's suppose at your house you bake a cake sometimes, okay, or you go to the market, you buy a cake. Now, in that cake, you will observe the outer surface slightly thin, very, very thin. It has got a different property, and the inside portion of cake will have a different property. So, think about the crust as that outside layer. It is very, very thin, right? It is the thinnest portion and also the lightest portion across the entirety of the planet. In fact, at the time when the entire planet was cooling down and it was getting converted from liquid to solid, at that point of time itself, you had the lightest materials, they came to the top. The heaviest materials, they settled down, they sunk down, and they formed the core, whereas the lightest materials such as silica, alumina, they came to the top and they started floating on the top. It is those portions which have solidified to form the crust that we see today. Then we have the middle portion, which is the most voluminous and the bulky portion as well. That is what we refer to as mantle. That is what we refer to as the mantle. And then in the innermost portion, you have the very hot core. Now, core in itself is not homogeneous at all. Core is the one where you have very high temperature which is experienced, but there also you have a distinction as outer core, and you also have what we refer to as the inner core. Okay, so as you start moving from crust to the region of the core, you experience a significant increase in temperature. That increase in temperature sometimes happens at a tremendous rate of 25 degrees Celsius temperature rise if you go 1 kilometer in depth and so on. So it varies with different depths of the planet, but nonetheless, this is a kind of a phenomena that you will observe from the outer surface to the interior as you move from the crust to the core. As one moves from the crust to the core, the temperature increases, and this is referred to as geothermal gradient. Gradient. Now, at the time when the planet was cooling down, we have discussed about it that the process of cooling was initiated on the outside. And slowly and steadily, the cooling down process reached the inner layers. But that meant that a lot of heat which was trapped in the inside, that heat continues to be trapped in the interior around the region of core till today. So that means the heat that was present at the time of formation of the planet, much of that heat or significant portion of that heat is still trapped in the interior of the planet around the region of the core. And that heat is what we refer to as residual heat. So when you talk about residual heat, it is the heat trapped in the interior since the formation. Residual means something which gets left behind, something which is remnant. That is what is referred to as residual heat. So, at the time when the planet was cooling down, it was cooling down from outside. The outside portions, they started solidifying. So, it was not as if only outer portion was the heated one. You had the inner portion also which was heated. So, as the outer portion became a solid, that meant there was not much of an avenue for the inner portion to lose its heat. So the heat got trapped in the interior. In the next couple of classes, as we will study everything, every phenomena that we see around us, be it the movement of continents, as the continents they move with respect to each other, be it the earthquakes that you experience, be it the volcanic eruptions that you experience, almost all of these phenomena, they are driven by this residual heat, that heat which is trapped in the region of the core. Now that is something which drives majority of the geomorphological or geographical phenomena that we experience on a day-to-day basis. Now here we have to understand another concept or another aspect, that is pressure. Now when we talk about pressure, pressure is basically the force which is acting from top on any unit area. Now, we have talked about the fact that the crust is the thinnermost layer. But when you walk outside and when you observe the nature around you, you observe these lofty mountains, you observe these very large rocks, you observe very wide valleys. And on top of it, if someone tells you that, look, this is the lightest portion, that only leaves it to your imagination that how heavy the materials present in the interior would be. But nonetheless, let's take the analogy from there itself. Suppose I tell you that do an exercise, go out on the road, pick up a stone and put it on your head and then walk. That stone will exert its pressure on you. Let's suppose you have done that. You have gone to the road, you have picked up a stone, you have kept it on your head and you are walking. You will be able to withstand that pressure, isn't it? Because it is very light, a stone. Then I tell you, now that you have done that, do one thing. Take a larger rock, place it on your head, and then try to walk. You will still be able to walk a couple of steps or 5 to 10 steps with that larger rock, right? Because the pressure is now more. Now, if I tell you that do one thing, pick up a small hillock on your head, just like what Hanuman did, do the same thing, and then repeat the process. Obviously, you will be squeezed under that pressure because the pressure is huge. Now, what I'm trying to get here at is greater the pressure which is imposed, lesser is the ability of the material on which you are exerting the pressure, lesser is the ability of the material to even carry out any significant change. Now, when there is so much of pressure imposed, that is something which impacts the state of material as well. How? So, for example, when we say any solid substance, let's assume. Now, that solid substance, if I heat it up, what will happen? If this solid substance is heated, it will melt. Now, in the case of the solids, if you look at the molecules, the atoms which are close to each other, they will give you a kind of a structure somewhat like this in the solid. Everything is bounded very close to each other. Now, when they will get converted into liquid, what will happen? These molecules, they will move slightly away from each other. So they will occupy some larger space. So can we not say that when the solid gets converted or melts into a liquid, it will occupy more volume? It will end up occupying more volume, isn't it? When the solid is molten into a liquid state, it will expand in size, it will basically occupy more volume. But imagine a circumstance, imagine a situation where by some measure or the else, let's suppose I have a solid. Now, from all sides, I'm exerting such a high amount of pressure that I'm not allowing the solid to expand at all. Now, in that case, if I heat it up, if I apply heat, will it melt? It will not melt, because for melting, it means the volume has to increase slightly. But in this case, there is no space for the expansion of volume at all. So that is why, despite the heat, the material will remain in a solid state. It will be a superheated solid state, isn't it? So despite the heat, it will remain superheated, heated solid. Now, why have I suddenly started talking about this? Of all the random things that I'm talking about, why have I started talking about this? That is because this is the exact phenomena at play when you come to the region of the core. As we move from the crust to the mantle to the core, the crust we know is in a solid state. The mantle is also in a solid state for most of its part. Now, when we come to the portion of the outer core, by that point of time, the temperature has increased to such an extent that outer core is something that you will find in the molten state or the liquid state. Liquid state. Okay, because the temperature is very, very high. Now, this molten state of core that you see, outer core, don't think that it is a thin layer. It also extends for more than 1,000 kilometers, right? It has got a width of close to around 2,000 kilometers as well. So there also it is significantly thick. By the time that you reach to the depth of the outer core and you reach to the level of inner core, the temperature is tremendously high. But at the same time, the pressure is also very high. And when you have very high pressure at that point of time, it means what? That the material cannot expand at all. And because the material cannot expand at all, so the material stays in the solid state as it is. So that is why the inner core, what you observe, is something which is going to be in a solid state. And the reason is very simple. Because of extreme pressure, materials are not allowed to expand, and stay in solid state. So that is what you end up finding in the interior of Earth in the case of the various different layers and the structure of the Earth as you refer to. Now, when we further dissect and when we further analyze the structure, overall, if you will observe, then the thinnest portion on the surface, that is what is referred to as the crust. And this crust basically was formed as a result of the lightest materials floating on top of the liquid earth, and those lightest materials solidifying and cooling down. So it will be an easy assumption to make that the crust basically constitutes the lightest part of the planet. It is a different matter altogether that till now in your lives, all that you have seen is the portion of crust only. Crust extends from the surface that we live on to a depth of around 20, 30, sometimes even 50 kilometers, not more than that. Then beyond that starts the mantle. And mantle extends up to a depth of around 3,000 kilometers from the surface. It is 2,900 kilometers from the surface, meaning northern extent of the country to the southern extent of the country, almost. So that gives you an idea about how thick the mantle is. Then after the mantle begins the liquid outer core, which again extends for a few thousand kilometers, and then you have the solid inner core. Now, the mantle is largely in a solid state. However, at a depth of around 150 to 200 kilometers from the surface, that is still very much in the mantle. So the crust is the topmost. Crust is the topmost, extends up till a depth of somewhere around 20 to 50 kilometers of depth. After that, mantle starts at a depth of around roughly 150 to 200 kilometers. (150 to 200 kilometers). It is still very much a part of the mantle, right? This is all a part of mantle itself. So at that depth, you have a layer which is partially molten. Underneath that, again you will find solid. Here again you will find solid. Here again you will find solid. But in that layer, you will find that you have the presence of partially molten or a semi-solid or a plasticky kind of a state, right? Which is stretchable, but it is not a complete liquid. It is a part liquid which is present. Please understand there's a lot of difference between a complete fluid and something which behaves slightly like a solid but also flows like a liquid. So it has got a flow because of very high temperature, but then here you don't have the absolute fluidity which is present here. Now, why is it that only in this region you have the extreme high temperature and you have the partial fluidity, whereas above it and underneath it again you have the solid structure? So it is in this region where you have extreme high temperature. High temperature. Now, because of that extreme high temperature, the layer that we are talking about, that becomes partially molten, stretchable, something which can move from one area to another very slowly like a molten solid. So that is why this is referred to as the weak layer overall, and it is also referred to as asthenosphere. Asthenos basically means weak. Asthenosphere, which is partially molten and semi-solid. Now the question arises that why is there a temperature anomaly which is experienced? Why is it that suddenly in this region you experience very high temperature? That is because at these depths, you find the presence of certain materials which are radioactive in nature. You find the presence of isotopes of potassium. You find the presence of isotopes of uranium. So that is why at these depths, you find the presence of presence of radioactive materials like isotopes of uranium and potassium. Now, you have these materials which are present, and then these materials, they experience very heavy pressure and weight acting from above, and also due to geothermal gradient there is a heated condition. So you have radioactive materials, you are extending or exerting a lot of pressure on it, and it is also experiencing a higher temperature at the end. So what will this lead to? This leads to the rise of thermonuclear reaction. So this gives rise to nuclear reactions, or thermonuclear basically means what produces heat at the end of it. Almost all nuclear reactions will always end up producing heat at the end of it. So gives rise to thermonuclear reactions. Now, these produce enough heat to partially melt the portion of asthenosphere. Okay. So that is why, because at this depth of around 150, 200, 250 kilometers, you have the presence of these radioactive materials. Owing to the huge weight exerted on them and the high temperature that they experience, these materials, they start melting, they start undergoing a thermonuclear reaction. That reaction produces a lot of heat, and as a result of that, the other materials that you find in the vicinity of that region, they start partially melting. They are not completely molten, and that is why it forms a weak layer in the otherwise solid mantle, and we refer to that as the asthenosphere in general. So that is the aspect of the structure of the earth in terms of the various different areas. Now, here, most of the volcanic eruptions that you observe, the molten materials that you find, they are mostly supplied from the region of asthenosphere in majority of the cases. It is a kind of a misunderstanding for many of us when we think that, okay, outer core is in molten state, so lava should be coming from outer core. No. Most of the molten materials that you see, which come out from the case of volcanic eruptions, they are supplied from asthenosphere. Now, above the asthenosphere also, if you will observe, you have some part of solid mantle. Below also you have some part of solid mantle, but above also you have some part of solid mantle. So the crust and the upper portion of solid mantle taken together, this is what is referred to as lithosphere. So when we talk about the term lithosphere, lithosphere is not only the crust or the surface, it also includes the upper solid portion of the mantle above the asthenosphere. Okay, right? So now let us take a look at each of these layers where you will get the written portion as well. That is something that most of us are concerned about, that regardless of the explanation, give us the written definition, and then you can carry out speaking whatever you want. So this is the written portion. When we talk about the crust, it is the outermost solid part of the earth. It is brittle in nature. Brittle means something which breaks easily, right? There are, for example, plastic will break easily, so it is brittle, right? On the other hand, for example, you have steel does not break easily, so it is not brittle. Okay, now here, it is the outermost solid part of the earth. It is brittle in nature. The thickness of the crust varies under the oceanic region and the continental areas. The crust in general that you observe, it is very thick in the case of the continental areas. It is very thin underneath the oceanic regions in general. Above around continental areas, it is very thick. In oceanic areas, it is very thin. Mean thickness of oceanic crust, if you will observe, is around 5 kilometers, whereas for the continents, it's around only 30 kilometers. This is the difference that you observe. Observe the thickness. But always keep one thing in mind, that regardless of the thickness that you observe here, it is the continental crust which is lighter. Always keep that in mind, that even though continental crust is thicker, it is still going to be lighter. And why is that? That is because of the materials that it is constituted or composed of. So, continental crust is basically thicker. At the same time, it is lighter. Oceanic crust is significantly thinner, very thin, but nonetheless, it will be heavier. Why? Because of the materials which constitute them, because of the density. If you want to find a similar analogy, think about it. For example, let's say you have a thick slab of, let's say, thermocol, and simultaneously you have a very thin slab of steel. Now, regardless of how thick a thermocol that you will get, still the steel slab will be heavier, isn't it? Why? Because the density of the material is different. Thermocol is having a lesser density. So here again, basically you will observe that the continental crust is thicker in areas of major mountain systems, for example, in the region of the Himalayas, because of folding and crustal compression. We have a crust which is as thick as 70 kilometers. Now, the continental crust, composed chiefly of granite, has a density of around 2.7 gram per centimeter cube, whereas that of the oceanic crust, which is constituted of basalt, there the mean density is around 3 gram per centimeter cube. It is around 2.9 to 3 gram per centimeter cube. So because the density of the oceanic crust is significantly larger, that is why oceanic crust is always going to be significantly heavier as well. Okay? Now, after this, when we move to the mantle, mantle is the portion. Now, by the way, when we talk about crust, crust represents only 1% of the mass. So this represents 1% of the mass. Okay? Think about it. All the mountain systems, everything that you have seen in your life till now, that ends up constituting only 1% of the mass of the planet. So what occupies more or greater majority of the mass? That is occupied by mantle. So the portion of the interior beyond the crust, that is referred to as the mantle. This entire region, immediately after the crust ends, the entire region that you see, that is mantle, extends up till a depth of around 2,900 kilometers from the surface. So here, it has got a density, mean density of close to around 3.4 gram per centimeter cube. But as you start going into the depth of the mantle, the density keeps on increasing. Sometimes it even rises out to the region of around 6 gram per centimeter cube, 6.5 gram per centimeter cube as well. Now here, in the portion of the mantle, you can say that it is largely solid, other than what we refer to as the asthenosphere. So basically, the upper portion of mantle, that is referred to as asthenosphere. The word astheno means weak. It is considered to be extending to a depth of around 400 kilometers, and it is the main source of magma that finds its way to the surface during volcanic eruptions. Now, why is it that this is a region which is weak? Because of presence of radioactive materials which undergo reaction to produce heat which partially melts the materials present. Please always keep in mind, above this asthenosphere also you have a upper portion of mantle which is solid. So if you, again I have to recall, so this will be the thin crust. Suppose this represents a kind of a crust of varying depth, obviously. Then suppose this is the kind of upper portion of mantle. This will be the layer of asthenosphere. Okay. And this will be above it, you will have solid mantle. This will be your crust. And this entire region will be considered as lithosphere. So I hope now, whenever you hear about the term lithosphere, you will never mistake it just as the surface that we stand on, because lithosphere represents something which is much more than that. Okay. Now, then when we come to the region of the core, so there the core mantle boundary is situated at a depth of around 2900 kilometer. The core basically makes up about 31% of the earth, right? Around 68% is constituted by mantle, 31% is by core. The inner core is in the solid state, whereas the outer core is in the liquid state. And why is that? Why is the inner core in solid state? Because of very high pressure. Very high pressure, due to which materials are not able to change the state. Okay. Then the core is made up of very heavy materials otherwise, such as nickel and iron, and that is why it is also referred to as a Nephe layer. Nephe in the sense that Ni stands for nickel, Fe in Nephe, that stands for iron. So it is very predominantly rich with iron and nickel. In fact, it is this layer of core which also subtends the magnetic properties that Earth indicates, what we also refer to as geomagnetism. Geomagnetism. Geo is something which refers to Earth. So geomagnetism refers to the magnetic properties exhibited by planet Earth. So planet Earth oftentimes ends up behaving like a magnet. So there you will see, just like in the case of a magnet, you have the field lines of action. Here also, the planet also ends up exhibiting magnetic lines of force, and the magnetic field also extends. So it starts behaving, or it does behave like a magnet because of the core. Why? Because you have presence of iron and nickel. But just the presence of iron and nickel, would that be a sufficient thing in order to initiate geomagnetism? The answer is no. The answer why magnetic field is exerted or exhibited, for all those who are weak in science or who have ignored science as if it is a kind of a step brotherly relation in your life. So if you have ignored science in your life, don't indulge in these intricacies. Just understand that, okay, earth behaves like a magnet because of the iron and nickel in the core. For those who are still curious enough, who are not afraid to embrace science and aspects of science, you can tickle your brain with the reasoning of it. So why is it that iron and nickel extends or does produce that magnetic field? The answer is very simple. We do know that the planet does rotate around its axis. Now, there is a continuous rotational motion involved here. Suppose this is the liquid outer core, you have the solid inner core. Suppose this is the liquid outer core. Now, as the planet is rotating, that liquid outer core, that will also be moving, right? It consists of iron and nickel. So that liquid outer core will also be moving. So just by the mere property of that liquid outer core moving in a kind of a circular motion, when you have magnetic materials, they move in a circular motion, they induce a magnetic field line which is perpendicular. So any of the time, and this is something which even Maxwell, you had the Maxwell's thumb rule basically, but ignore all of that. So you had various important people who have earlier in the past, they have told about the relationship between movement of particles and magnetic field lines. So just remember, any of the magnetic materials, when they move in a kind of a circular motion, they will always exert or represent a kind of a magnetic field. Magnetic field. So you have the particles of iron and nickel which keep on moving like a solenoid in general, or ignore solenoid, just think about it, that they keep on moving in a circular motion, and that is what generates a kind of a magnetic field, right? So the magnetic field that you see across the planet, that is basically an outcome, a resultant of this movement of particles in the liquid outer core. Now, this movement of materials or this movement of outer core, that also many of the times brings about certain changes and certain dynamism involved. How? So basically, this outer core is made up of liquid iron and nickel. But this liquid that we are talking about, this is not like your jar of water that it can flow easily from here to there. This is also consisting of large blobs of some amount of semi-solid particle, some amount of semi-solid iron, some chunks which have greater concentration of material, some chunks where materials are completely fluid, some areas in the outer core where materials are partially fluid. So it is not a kind of a homogeneous mixture. Sometimes what happens, that the concentration of iron and nickel in the outer core during this movement, that undergoes a slight change. I will repeat, because the liquid outer core is not a uniformly distributed liquid, during this rotation, sometimes what happens, you have some portion of the outer core, the distribution of iron and nickel, sometimes it gets disturbed. That means in certain areas there is an overwhelming presence of iron and nickel, and in certain areas there is a lacking of it. So as a result of it, sometimes you will find that here you have an overwhelming presence of iron and nickel. Sometimes it shifts, and here you have the overwhelming presence. So that basically brings into effect a situation where these magnetic field lines extended, they also change. Now, these magnetic field lines that are extended, they represent what we refer to as the magnetic poles of the planet. Magnetic poles of Earth. Okay? How many of you have not understood? Okay. Okay. Fair enough. Vijay, did anyone went inside the planet Earth? If no, how can we know about the core? Think about it. Think about it. Apply your logic. What can be the reason? How do we know about the interior of the Earth? Have we sent someone? Have you read somewhere that someone reached the inner portion of the core and they recorded the temperature and they got back? Have you read about it somewhere, or from your childhood days have you heard about it? No. So if you have not heard about it, that means obviously nobody would have gone to the center of the Earth. Then how do we get to know about the portions of the interior? That is where I'm sure in that portion you would not have paid attention. That is why I say always pay attention, that you have the direct and the indirect sources. It is with the help of the direct and the indirect sources that we get to know about the interior. It is with the help of the indirect sources such as seismic activities where we get to know what is constituted in the core. What is present in the core, we get to know by the indirect sources, for example, seismic activities. Okay. Outer core, why in liquid state, Preetham? That is because of very high temperature experienced. Okay. Right. So, in the portion of core, we have basically discussed till now that outer core is in liquid, whereas the inner core is in solid state. Why is inner core in solid state? Because of the very high temperature experienced. That is where the inner core should also be in molten state. But simultaneously, from all different sides, you have thousands of kilometers of pressure acting, due to which the portion of the inner core does not get any space to expand at all. So, because and when a solid does not get a space to expand, will it get converted into liquid? Absolutely not. So, that is where you will find that the region of the inner core is still in a solid state. Nonetheless, the outer core is in liquid. Now, when the planet rotates, the outer core, which is in liquid, will also rotate along with the planet. That means the liquid which is present, that will be moving in a kind of a circular motion. Now, this liquid consists of materials such as iron and nickel. Now, these materials are at very high temperature. When you keep moving them in a circular manner, that generates a magnetic field which is perpendicular to them. So that is why here, as the circulation takes place, as the rotation takes place, it generates a kind of a magnetic field of action. And that is what we refer to as geomagnetism, or the magnetic field exerted by the planet. Okay, right? How much area is constituted by the outer and the inner core? You will get to know by this image. This image, that is why I have attached here. You will get that the overall radius is around 6371 kilometer. What is the depth at various different portions? All of that around 2900 kilometers is where you have the outer core which starts. Then furthermore, the inner core starts for the later on. So at 5100 kilometers is when the inner core starts. So that means outer core is around 2200 kilometers thick, and that also means the inner core is around 1200 kilometers thick. Okay, right? Now, after this, we come to the portion which we refer to as the discontinuities. Now, what do we mean by discontinuities? Now, let us understand this. So, when we start going into the depth, when we start going into the depth of the planet, basically, it is not as if the type of material that you will experience on the surface, that will be the same kind of material that you will experience 100 kilometers lower. No, at a depth of 100 kilometers, there will be a significantly greater amount of pressure which would be acting. There would be greater amount of force which is exerted in general, isn't it? So when you have greater amount of pressure, greater amount of force which is exerted, Then what is the outcome in that situation? In that situation, the outcome that you will observe is that materials, the type of materials, the densities of materials, etc., they start changing significantly. So basically, as you move from the surface to the depth, the type of materials, they change, their densities change, the particle arrangement changes. And these different states or these different densities of materials, even in the region of crust, as you go to the depth of the crust, the materials that you expect in the lower portion of the crust, they will have a different formation as compared to the materials formed on the top of the crust. So that is where all these different materials, they are separated by a layer beyond which suddenly the material type, density, etc. changes, and that is what we refer to as discontinuities. So discontinuities are those portions in the interior which basically signify a sudden change in the type of material, density of material, arrangement of particles, etc., as we go into the depth. Okay. So these are those places in the interior or demarcations, not demarcations exactly, regions in the interior where the material density, particle arrangement, etc., undergo a sudden change with depth. Okay. So here, for example, in the region of the crust, the upper portion of the crust and the lower portion of the crust, they have a different material. So that is distinguished by a discontinuity that we refer to as the Conrad discontinuity. It separates the outer and the inner crust. Then the crust is separated from the region of the mantle with the help of what we refer to as the Mohorovičić discontinuity, or in simple, Moho discontinuity. This is Mohorovičić discontinuity, or simply put, Moho discontinuity, sometimes also referred to as simply the moho, right? So then you have the upper mantle and the lower mantle. That is again something separated by a discontinuity, that is the Repeti discontinuity. Obviously, in the lower mantle, the density of materials will be much greater. Then the mantle is separated from the region of the core itself by a discontinuity that we refer to as the Gutenberg discontinuity. So that is what is the Gutenberg discontinuity. In general, it separates the mantle and the portion of the liquid outer core. And then the liquid outer core is separated from the region of the solid outer core, solid inner core, because both of them are in different states of material altogether. So that is separated by a discontinuity referred to as Lehman discontinuity. So this is something which is going to be relevant for your prelims examination. In general studies, you don't expect a detailed questions to be subjective question to be framed from this area. So that is why this is an area which is relevant for your prelims examination in general. And even for your prelims, if I have to mark out the important ones, so the Moho discontinuity is important, Gutenberg discontinuity is important, and the Lehman discontinuity is important, in the sense you should be able to know that Moho distinguishes the crust and the mantle, Gutenberg distinguishes between the mantle and the outer core, and Lehman distinguishes between the outer core and the inner core. This much idea you should have. Okay. Then from this particular portion, another kind of question that you see asked in prelims sometimes, even though very rarely nowadays, that is about the abundance of materials and elements in the interior of the planet. So in that case, when we talk about minerals in the interior of the earth, so here, if you consider the entire planet, in that case, earth as a whole, if you consider, iron is one of the most abundant elements which are present. So when you consider the entire planet or earth, iron is most abundant, followed by oxygen. And we are talking about the earth, we are not talking about atmosphere here. So the oxygen that you see here, that is basically found in the form of compounds, in the form of oxides, that is to be found. For example, silica is silicon and oxygen. Alumina is aluminium and oxygen. So all this basically ends up creating the abundance of material. So most abundant is iron, followed by oxygen, followed by silicon, followed by magnesium. Ideally, for the examination perspective, you as a candidate should be aware of the top four. Then the materials that you find only on the surface, only on the earth's crust, not the mantle, not the core. So when you consider only the earth's crust, at that point of time, the most abundant element is oxygen, followed by silicon, followed by aluminium, followed by iron. Again, the top four. So this is something which is relevant for your prelims. Okay. Why will nitrogen come here? Nitrogen is present in atmosphere, right? This is the crust, the surface that we are talking about. Okay. Short form to remember? No, I am not the individual who will give you short form like BB Roy went to Great Britain, etc. Those acronyms, you guys are much smarter than me. So those acronyms, I'm sure you will be able to extract on your own in a much better way than what I will be able to do so. So please do that on your own. Now, then we come to the portion of rocks. Now, from the portion of rocks, as we have already talked about, this is something which is relevant for your prelims. And sometimes questions from this are asked in the mains examination as well. Very simple questions and direct questions are asked. For example, in 2022, in the mains examination, you had the question in geography that what do we mean by primary rocks? Tell us about their properties. So sometimes basic questions from these rocks can be asked. So when we talk about rocks, rocks are basically aggregates of various different mineral and constituents that you see. Rocks are never composed of only one type of material. Rocks generally will be an accumulation of all the various different types of materials considered together in many of the cases. So here when we talk about rocks, basically they are mineral aggregates with a combination of properties of all the various constituents which you find in these rocks. And also any unique combination, composition, grain size, texture, etc., that basically creates the distinguishing features in between the rocks. Now, for general studies, you don't need to read that in significant amount of detail. The basic understanding of what these rocks are, that also will suffice in many cases. So when we talk about the types of rocks, the basic classification is done on the basis of formation. On the basis of formation. Devansh, we will study that when we come to earthquakes, my dear friend. Please have patience for a couple of more days. We will study that. Okay. Right. North Pole is exactly or tilt. No, magnetic pole and North Pole are slightly different, Sarthak. Yes, Swaroop, that is the case. We'll talk about it. What the various different rocks mean, we'll talk about it. Don't worry. Hemant, I will end the session early today. Don't worry about it. The more you remind me about it, maybe I'll extend it for an extra session. Generally, I have a target of finishing the session at least 5 to 7 minutes early, because immediately after this, I take the webinar as well, the mains based current affairs. So we will be ending the session early, don't worry. Now, when we talk about the rocks, they are basically classified on the basis how they were created. So, for example, we talk about the igneous rocks, suppose. Now, igneous rocks, they are also referred to as what we refer to as primary rocks. Primary rocks. Primary rocks means the rocks which were created first. Now, when we talk about igneous rocks, igneous means what? Something dealing with fire. That is the meaning of igneous, isn't it? So, these are the rocks which are formed as a result of cooling down of lava or the molten materials. Sometimes the molten materials, they get solidified or cooled down in the region of interior of crust itself. They are unable to erupt as a volcanic eruption. So there only, in the interior only, they will form igneous rock. So these are the rocks formed as a result of formed as a result of melting or solidification of molten lava or magma. Okay. Now, whenever the lava or magma solidifies, it will form a rock. You know, in the very initial days when the planet was getting created, in the very initial days, around 3.5 billion years ago, 3 billion years ago, we have talked about the fact that in those days, the planet was covered only with water. And there are various different research papers and researches which have told us that at that point of time, planet was completely covered in water. At that point of time, you had underwater volcanic eruptions which kept on happening. And I hope we are aware of this, that underwater volcanic eruptions, they do happen. They do happen across the planet, whether you consider the region of Atlantic Ocean, whether you consider some portions of Indian Ocean, whether you consider the portion of Pacific. Underwater volcanic eruptions, they do happen. So when these underwater volcanic eruptions were happening, eventually few of these, they erupted and they kept on accumulating till they breached the water level. They emerged out of water, and these volcanic eruptions continued, and you had molten lava which would come out, which would solidify. And that is how the first land on the planet, that is how they came into existence. So whenever a new land gets created, it is always the igneous rock that you will find there. In fact, as and when we come to the portion of Indian geography, I will also talk about how some portion in the southern part of Jharkhand and some portion in the western part of the region of West Bengal, that is in the region around Singhbhum region of Chota Nagpur Plateau, that is considered to be one of the oldest land masses across the entirety of the planet. It is estimated that at one point of time, when that region would have been created, there would have been nothing but water all around, and that would have been created as a result of volcanic eruptions. It is estimated that the present day region of Jharkhand and northern Odisha and western part of West Bengal that you see, at one point of time, it would have been like an island with large sandy beaches. And how do we get to know about all this? Do we have someone showing us a documentary and telling us about all the evidence? No. We get to know this by studying the rocks. It is by studying these rocks, by the grains, their granular structure, that we get an idea about how, not only how old a rock is, but also the details of its formation. So that is how you have the igneous rocks which get created. Then igneous rocks, let's suppose, have been created in a region. Now, in that region over a period of hundreds, thousands, and millions of years, obviously there will be a lot of rainfall, maybe river action, lot of winds which will be blowing. Now, as a result of all this, what will happen to the structure of the rock? It will weaken. Many of the time, the larger rock will be then reduced to smaller particles. And all those smaller particles or deposits you will find to be present in one area. All these, let's suppose, deposits. Even the river, when it flows, if ever you have been close to a river, you'll find that on the sides, the river keeps on depositing sandy materials and so on. Now, over a period of many hundreds and thousands of years, these deposits, they start to get compressed. When they start getting compressed, slowly and steadily, they start undergoing a kind of a solidification. And that is when eventually you have the cementation and they turn into solid rock like structure. So when we talk about sedimentary rocks, these are basically solidified deposits. These are formed as a result of compaction, cementation of the deposited materials. Okay? Then you have metamorphic rocks. Metamorphic. The term arises from or is derived from the terminology metamorphosis. What is the meaning of metamorphosis in English? It means a kind of a change, somewhere where you have a drastic change. That is what is metamorphosis. So when we talk about metamorphic rocks, these are basically the igneous or the sedimentary rocks which have changed their state of presence, which have changed the kind of particle arrangement, etc. And when they are exposed to high temperature and pressure, they completely change their properties and they become a new rock altogether, that we refer to as metamorphic rock. So here, when the rocks are exposed to high temperature or high pressure, they change into a different rock type altogether, and that is known as metamorphic rocks. Okay? So, cooling down of lava or magma, igneous rocks; solidification of deposits, sedimentary rocks; the existing sedimentary or igneous rocks changing their state due to high temperature and pressure, metamorphic rocks. Now, here think about it logically now. When we say that in which of these rocks will you be able to find fossils or remains of animals or plants? Will you be able to find fossils or remains of animals or plants in igneous rocks? Do you think yes or no? In igneous? Good. In igneous, you don't find any fossil remains. Why? Because it is something which is formed by the cooling of lava or magma, and there you don't have fossils or plant or animal remains in lava or magma is not present at all. Then, when we talk about sedimentary rocks, they are formed as a result of the deposits coming together, cementing together, and forming a rock. There, can we have the presence of fossils of animals or plants? Yes, absolutely yes. Why? Because amongst these layers, it can absolutely be possible that you have one plant or one animal remain which gets left behind. So, there it is absolutely possible. So, that is where in sedimentary rocks you will find rich evidences of life, whereas in the other ones you don't find it. Lava and magma is different. When molten materials are present in the interior, they are about to come to the surface, they are magma. When they come to the surface, they are referred to as lava. Okay, so we will study about these rocks in greater detail tomorrow, and that is when we will be taking a look at the types of igneous, types of sedimentary rocks as well. With the help of the image, we will try to understand it, and then we will be moving on into the portions of continental drift and plate tectonics. I would advise you guys that till that point of time, try to read through and look through the PPT and try to understand the portions that we have already covered. Many of you have not attended the first session, so for all of those, cover the portions till now that we have covered, and we meet again in the next class. We carry it forward. Okay, now a couple of questions we'll take and we'll end it up. Sedimentary rock, Pritham, has been formed as a result of the deposits from various different other rocks. When the river flows and carries the other rocks, they get deposited in some places. Many of the time, the remnants of other materials, sand, etc., gets deposited. Now, all those deposits over a period of 100,000 years, they lie in a place. They slowly and steadily they start solidifying. That is how you have the sedimentary rocks. Map pointing, Shravani, next class. Mains question, Swaroop, in many of the cases, mains questions are derived from geomorphology. If you get a mains question, it will be very direct sort of mains question. We'll discuss that as well. Arti, generally in the case of the sedimentary rocks, that is where you will find. Earth's core is cooling with time, Monica. That is true. Supernova magnetic and gravitational anomalies, basically the planet, the gravitational force, the magnetic force, for all of them, core is responsible. So whenever these change even slightly, so that gives an idea to us that something might be different in the core. So we study the core again. So that gives us an idea, further insight, that how the core tends to behave. So all this is what? Information about the interior. Devansh, no, they are not found in metamorphic rocks. Radioactive materials are basically the materials that undergo radioactive reaction, where the materials can break down into two smaller objects, etc., into two smaller atoms. That is radioactive. Till now, whatever we have studied, Abhishek, there is not much of a main type of question which can be asked other than what are the sources of information for the interior of the planet. Okay. Magnetic poles of the earth, basically these are the magnetic poles basically are the ones where you will find that uh, from the interior you have magnetic field lines which extend, and that is what the magnetic poles are. So that is where we'll restrict the session here today, guys. We'll meet again in the next class. Till that point of time, do take care of yourself. Thank you. If any question does prevail, feel free to write to us and we'll get back to you. Okay.